This is a brief presentation covering some of the key concepts behind my graduate research in applied math at UC Davis. We'll start with motivation. Classical signals can be viewed as signals lying on very simple graphs. For example, on the left, we have a one-dimensional signal, which could be part of an audio signal. On the right, we're visualizing the signal as lying on the nodes of a path graph. As another example, we can think of the pixels of an image as lying on the nodes of a regular two-dimensional grid, as you see here. The goal of my research was to extend techniques that exist for classical signal processing to this new and more general setting of signals on graphs. Here, I've shown a couple examples of graphs which are easily visualized. On the left, we have some traffic data on the Toronto road network. For this graph, the nodes correspond to intersections, the edges correspond to roads, and the values on the nodes are the traffic volumes over 24-hour windows. On the right, we have a graph of a dendritic tree. The graph itself shows the structure of the tree, and the values at the nodes are measurements of the thickness at those points. To explain the underlying idea behind my research, I posed this question: how would you get a third grade class to paint this? I would argue that the best strategy is to assess the painting abilities of the students and assign portions of the image accordingly. You've probably got a few kids who are really good at painting, but they take a long time, so they'll paint the small, high detail regions, such as the head, the hand holding the torch, and maybe parts of the base of the statue. On the other hand, you've probably got a few kids who are fast but sloppy when it comes to painting, so you'll have them paint the large, low detail regions, most notably the sky. This strategy delivers the two qualities that we're after: accuracy and efficiency. We can use this same idea for analyzing signals on graphs. In this very simple example, what I've done is to take the signal on the entire graph and decompose it into the four subsignals on the right. The reason for doing this is that it may be more efficient to represent different portions of the signal that have different characteristics separately rather than collectively. Obviously, this is a very simple example, but it demonstrates some of the underlying logic behind the methods that I've developed. As a summary, what I've developed are methods and software for analysis. So we've got this new kind of signal. How do we analyze it? How do we make sense of it? What can we learn about it? Methods for denoising. Maybe the signal has some noise in it and we want to clean it up. How can we do that? I've developed methods and code for visualization. This goes hand in hand with interpreting the analysis, because really what we've got is a long list of numbers, and we need ways to figure out what these numbers are telling us, and obviously a lot more. Some applications of my work are traffic data, where the roads and intersections give us the structure of the graph, and we want to know how we can figure out patterns in the data. For example, maybe we ask, how can we improve the road network? Another example is social network data. So someone on Facebook or LinkedIn could have hundreds of connections, which generates a very complicated graph structure. How can we analyze data on that network? How can we learn useful things? Another application is recommendation systems. Along the lines of social network analysis, one of the ways we can recommend things is to identify people with similar interests and use one person's preferences to recommend to the other, and vice versa. A little bit more of an abstract application would be machine learning in this general graph setting. For example, these methods could be applied to the problem of classifying nodes in the graph. Skills that I've cultivated include the ability to tackle challenging and open-ended problems, because this is a relatively new field and no one had done something along the same lines as I did, so I had to come up with the mathematical ideas and the coding strategies myself. I've demonstrated the ability to analyze complicated data and to do so in a way that is meaningful and transparent. While the methods and tools that I've developed are complicated, the underlying ideas are simple, and you can explain them to people and they make sense. You have some notion of what's going on with the code, as opposed to methods that are hard to understand and thus hard to interpret their results. And last but not least, I've demonstrated the ability to write high-quality code that is easy to use. Much of the code that I've come across is difficult to understand and use for yourself, but I take a lot of pride in writing code that is cleanly written, that runs efficiently, and it's easy for someone to just jump right in and start using it. And in fact, my code could serve as a framework that other researchers could use to implement their own methods. This concludes the summary of my research. Thank you for your attention.